So the material sent to you, you have already gone through. And so some idea you have.
So can you see the slide?
Yes,
Yes,
sir.
sir.
All of you, right? And the audio is also clear, I hope.
मेरे लिए
Yes,
तो
sir.
Yes,
ठीक है
sir.
सर.
Okay, good. So let's try to finish this quickly. So our great virtual fieldwork. Unfortunately, we have to do it this way. Acha, somebody is talking. Please stop that. Somebody is talking with his mic left on. Yeah, thank you. Okay, so see what we would have done had it been an offline fieldwork. So we would have taken a field transect, okay, across a Creighton mobile belt contact. So in this case, the usually because it's nearby, we take students to the Singhum Creighton. Okay, nearby Singhum Creighton. Some of you may have heard the term. Singhum is a district in, I think, Jharkhand. There are two districts. And so the crater is named after that region. It's called the Singhum crater. And if you look at this Google Earth image, so I have roughly demarcated, okay, using lines, the the Singhum crater to the south, okay, this area here, so this entire thing, and then you have what is called the North Singhum mobile belt. Okay, I will explain these terms little later on. What is a crater, what is a mobile belt, and to the north of that you have the Chota Nagpur Nice complex. So usually when we do field work, we take a transect somewhere across like this, across the so from the crater into the mobile belt. So what we will do today is we have been to the field, we have collected some photographs of the rocks and maybe a couple of videos as well. And I will just try to explain in the next 30-40 minutes of what are the geological features that you have, what are the rock types that you have as you take a transect across the crater into the mobile belt. Yeah. So that is all that we can do virtually. Rest, if you get a chance, you can come to the field and then we can see what we actually do in the field. So now this is a map that you see here, which shows the same thing, the Singhum craton. It is this oval shaped part. So craton here, okay, so craton refers to a very stable part of continents. Most of it was already created in the Archean, okay, Archean era. So what is the Archean? The Archean is the time period between roughly 4 GA and 2.5 GA. Okay, so that is the time period between 4 GA and 2.5 GA. So most of this part of the continental crust, okay, the part that we call the craton, this was created in that time period, and since then it has not undergone any significant deformation, remelting, or what we call as crustal reworking. So they have become very stable parts of the continents, and they are usually not nothing much is happening geologically. Okay. Since nothing much has happened geologically since about 2.5 G. So that is how we define a craton. So in eastern India, we have a craton, uh, which is called the Singhum craton. This occupies parts of Orissa, Jharkhand, and I think mostly Orissa and Jharkhand. And the mobile belt is an orogenic belt. So what is an orogenic belt? It's a belt of rocks which are produced due to volcanism and deformation or tectonism happening when you have compression. So you have these are elongate terrains formed due to compressive tectonic forces, as a result of which you have extreme deformation of rocks, you have magmatism, and ultimately leads to the building of mountain chains. Okay, for example, the Himalayan mountain chain that you have, it's a very modern orogenic belt. So similarly, you had orogenic belts forming in the past. Today they may not appear as high as the Himalayas, but at some point of time, many of these orogenic belts had rocks or had terrains with very high topography. But today, most of them have been eroded away, and you just see you're left with the rocks of the middle or the lower crust exposed. So, this is what are orogenic belts or mobile belts. These are orogenic belts formed due to in a compressive tectonic regime when you have either an island arc or a continental arc accreting with a continent, or when you have two continents colliding with each other. So all the rocks that you have in such orogenic belts, they have undergone extreme deformation, okay, as a result of which they uh, produce secondary deformation structures, planar structures, linear structures. You might have heard of terms like schistosity, foliation, nisosity, etc. These are secondary planar deformation structures which are produced, and the rocks have also undergone high-grade metamorphism. So, so in this case, the orogenic belt that we are looking at, it's called the North Singhbum Mobile Belt. Okay, so this is an orogenic belt which is essentially uh, sandwiched between the Singhbum Craton to the south and this is the Chotanagpur Mice Complex to the north. Okay, in between these two, you have a relatively narrow zone of or band of rocks. Roughly, I think widths are variable, but in the range of I think 20-25 kilometers at the most. So this is the North Singhbum mobile belt. Now the contacts between the Singhbum Craton and the North Singhbum mobile belt. So this contact here, okay, this contact here, as well as the contact between the North Singhbum mobile belt and the Chotanagpur Ice Complex. These are all tectonic contacts. These are all tectonic contacts, and these tectonic contacts are marked by shear zones. Okay, shear zones are zones where rocks have undergone very high finite strain. Okay, so these are zones along which there's lots of strain, and this strain is in response to the deformation and the compression that happens when these uh, these terrains collide and merge or amalgamate together with each other. So the shear zone that marks or passes close to the boundary between the Singhbum Craton and the North Singhbum Wild Belt, this shear zone is called the Singhbum Shear Zone, SSZ, Singhbum Shear Zone. Okay, the Singhbum Shear Zone. Now, the Singhbum Shear Zone, it's an arcuate zone, and it's fairly well known in geological literature because this is the location of very important mineralization, especially of uranium. Okay, and then we also had mineralization of copper, I think. Uh, so
Yes, copper, even some amount of gold, etc. are there. And also
sometimes
this
yes, some gold.
river Suvarnarekha name comes from the gold occurrence somewhere, and it comes in the river sediment.
Yeah. So primarily the mineralization is of the strategically important metal uranium. Okay, there are several active uranium mines. For example, you might have heard of Jaduguda, Narwa Pahad, Bhatin, and so on. So these are active uranium mines all along this shear zone, okay, at several places. So that is why it's important. The shear zone between the North Sea Mobile Belt and the the Chotanagpur Gneiss Complex. This is called the South Purulia Shear Zone, okay, or the South Purulia. South, it's Purulia. Purulia is a district in Bengal, in that region. So, South Purulia Shear Zone. Okay, that is the so South Purulia Shear Zone. Now, the let's look at, okay, so we will look at one unit at a time. So we start with the Singhbum Craton. Now the Singhbum Craton, so comprises of very old rocks. Okay, these comprises of rocks which are having ages from the Paleo-Archean to the Neo-Archean. So Paleo-Archean starts somewhere about 3.6 GA and the Neo-Archean ends at about 2.5 GA. Okay, so you have rocks of this age that make up the Singhbum Craton. And most of these rocks that you have, they are essentially mostly granitoids and supracrustal rocks. Supracrustal rocks means rocks which are deposited above a basement. Now, if you look at the granitoids, so granitoid is a clan of rocks comprising essentially of a large variety of different types of felsic plutonic rocks. Okay, so the granitoids that comprise the Archean crust or the Archean cratons are mostly of two types. The first type, which represents a very characteristic association that is commonly seen only in the Archean cratons, is referred to as, or dominantly seen in the Archean craton, is referred to as the tonalite phongiomite granodiorite series or the TTG series. Okay, so this is the characteristic series of granitoids. I will explain what these are a little later on. This is the characteristic series of granitoids that are found in that were formed in the Archean. Okay, and the second group of granitoids that you have are K-rich granites or potassium or potassic or potassium-rich granites. Now the TTGs represent the characteristic Archean, Paleo-Archean to Neo-Archean association, and the K-rich granites are usually younger. They are mostly of Neo-Archean age. And the supracrustal rocks, they occur as arcuate linear belts, and they are mostly made up of either metavolcanic rocks, so metabasalts, komatiites. I'll explain these terms a little later on, and metasedimentary rocks. Okay, so these are metavolcanic, mostly metabasalts, andesites, and some komatiites, which are ultramafic rocks, ultramafic volcanic rocks, uh, containing elongated blade-like skeletal crystals of olivine. Essentially, this is an ultramafic rock or ultramafic volcanic rock. Okay, you get, I think there is only one occurrence of post-Archean komatiites. So this is another characteristic feature of the Archean cratons, that you have ultramafic volcanic rocks being produced. To produce ultramafic volcanic rocks, you require very high degrees of partial melting of the mantle. That was only possible in the Archean time. Why? Because the geothermal gradient in the Archean was much higher, because the Earth was much hotter. Okay, so potential temperatures of the mantle, for example, were at least 2 to 300 degrees Celsius higher. So you could melt the mantle to a greater degree and produce komatiites. Modern times, the Earth is cooled, the geothermal gradient is much lower, and therefore, in most tectonic settings, the geothermal gradient is too low to melt the mantle in significant amounts to produce ultramafic magmas. Okay, so one group of the supracrustal rock comprises the volcanic rocks, and the other group comprises sedimentary rocks, the shale, banded iron formation, quartzite, etc. Now these are all metamorphosed. They are metamorphosed to relatively low grade, so green schist facies condition. So if you people have questions in between, you please ask. Don't just sit there like a dumb guy. Huh? If you have questions, you ask. Okay, so let's look at what these TTGs or the tonalite transgemmite granodiorites look like. Okay, as I said, these are TTGs are archean granitoids. They are formed by partial melting of metabasaltic rock. So you take a basalt or metamorphose it and you partially melt it. The melts that you produce, if you melt it at the right depths and at the right degrees, then you produce melt similar in composition to the TTGs. Now, if you look at this diagram here, this is the ternary diagram of Baker, which which tells you which gives you the differences in the composition of the different types of granitoids that you have in terms of the uh, anorthite, albite, and orthoclase contents. So you see that you have the tonalite field here. So that is where this tonalite of the TTG group plots. Yeah,
Yeah, probably the Asi say this only it is stock at one screen only that it is original screen. Can you make it that yeah, presentation mode?
yeah. This is in now. Can you see?
Mm.
No, sir.
No.
No.
Yeah, go to the presentation. I think that it is not in the presentation mode that
No,
panel.
no,
No?
no. It is. This is how I used to teach.
Now it has changed now. But
Yeah, but
probably on the left side you have gone to different screen. So that's why
no, no. I think this is a problem of Google Meet.
maybe.
Because
So, your screen is black now. Probably you can stop sharing and then reshare.
yeah, yeah. In because I'm using a tablet, okay, for a pen tablet for writing, and in in the Microsoft Teams it used to work, but I don't know why here it's not working.
Yeah, probably it is now in the triangle is there. Tonalite, transamite, granodiorite.
Hmm.
That screen is visible now, but
Yeah.
not in the full screen mode.
Not in the full screen mode.
Mhm. On the left hand side, all those different slides are visible.
No, so it's okay. Let me bring it to the other one.
When you are changing the slides, it is coming actually.
Now,
It is that basalt. Hmm. That
नहीं,
screen.
now
नहीं वो बसल्ट वाले में अटका है
आएगा आएगा. अभी where is it now?
हाँ वही सुप्रा क्रिस्टल बसल्ट now the TTG.
Hmm. So can you see it now?
It is on the TTG screen.
Yeah, yeah. Now how do I make it full screen? More option. So can you see the pointer now?
Yes, it was visible for a bit.
It's visible.
So can you please move the cursor once again? So
Anyway, I think you have to stop using the cursor. Hmm. So can you see now? I put a plus.
Yeah.
Can you see the cursor? Nothing.
Mhm.
no, sir, nothing.
Okay. Can you see the slide?
Yes, the slide is there.
Okay. So let's go ahead with the slide. Okay.
Mm.
So the TTGs, these are Archean granites or granitoids. They are formed by partial melting of metabasalt. So you partially melt a metabasalt and you'll produce a TTG. Now, what exactly are TTGs? If you look at this triangular diagram, which shows which is used to discriminate between the different types of granitoids on the basis of on their normative anorthite, albite, and orthoclase content. So what you see is that the tonalites are the ones which have the highest anorthite content, whereas the granites are the ones which have the highest orthoclase contents. Strongymites, they have plagioclase, but which is more albitic. And in between the tonalite and the granite, you have the granodiorites. So the granites generally they are more orthoclase OR, and therefore that is they are potassic. So they are more potassic, and the TTGs they have less of orthoclase, and therefore they are more sodic. Because they have more of plagioclase and less of K feldspar. Therefore, the TTGs are defined as granites with K2O by Na2O ratio less than 0.8. Now these are the oldest felsic components or felsic parts of the craton. That means this is the oldest or the earliest continental crust that was produced in the Archean. And this felsic crust was largely created. At least it is believed that at least 50 to 60% of it has already formed, by 2.5, and it happened in very short but short-lived but several episodes which involved magmatic accretion, tectonic thinning, and partial high-grade metamorphism, which accompanied the partial melting of the metabasalts. Okay, as I said, most of this TTG crust or this granitic continental crust was already produced to a large extent by 2.5 billion years. So, because these represent the earliest felsic crust, and since the continental crust is made up of dominantly of felsic rock, so the Archean TTGs, they preserve the archive of the earliest phases of the building of the continents, and that is why they are of such great interest to people who study earlier processes.
Yeah, you see, Dr. Upadhyay told that these TTGs are produced because of partial melting of basalts. Huh? So basalt is metamorphosed and then partially melted to form these TTGs. So the natural question is, what happens to the partial melting of the granites at this time? The question does not arise because the granites were not there. Okay. Now, okay, Devasisi.
Yeah. Okay. So now, if you come to the supracrustal rocks, so the supracrustal rocks, they are collectively, they're referred to as greenstone belts. Now, the reason why they are called greenstone belts is because of the greenish or bluish greenish appearance of the mostly the metabasic rocks. Why they are why they have this bluish or greenish appearance? Because these basalts, as I mentioned earlier on, you can look at this image here. Okay, these basalts. So this I'm showing you a video. Can you see the video, all of you?
It has not come.
I think it's freezing. Anyway, I think I have given the slides, right? So you people can watch it yourself. Huh? So these basalts. Most of these, yeah.
Sir, the study material which is provided, the link, it has expired, so we are not able to download the study material.
So who told you not to download it? Expired. Some of you might have downloaded it. And has anybody downloaded it? Hello. Has anybody downloaded it? Yes or no?
Sir, if it is possible, can you please resend the study material?
No, I will not send it.
So I
It's
have,
one.
so I have it. I have it.
Good. Then you can share it to others. Okay. What's your name?
So Gargi.
Good. So all of you, you asked her to share it. It's a large file, and I have to go through WeTransfer and all these things. I will not do it again. So it was active for 1 week. The link was active for 1 week, right? Okay. So the basalts, they get metamorphosed to greenish species conditions, and therefore they comprise the igneous minerals get replaced by secondary hydrous minerals, green colored minerals like chlorite, epidote, actinolite, hornblende, zoisite, clinozoisite. This is what gives them the bluish green, greenish appearance of the basalts, etc., in the supracrustal belts, and that is why they are called greenstone belts. Now, basalts, as you know, if you look at these basalts under, if you look at thin sections under the microscope, they could be fine grained, almost glassy, or recrystallized, or they could be porphyritic. So this is what they look like under in the microscope. So you can see these are phenocrysts of plagioclase as well as
Yeah, the
pyroxenes.
screen
Huh?
has not changed, I think.
Now,
No, sir.
no.
See at that TTG one.
Not changed.
Now it has changed. It has come to that thin section.
Yeah, okay, good. So, this is what the basalts look like. I've just put it just to kind of refresh your mind. Since you people are geophysics students, you might have forgotten what basalts are. So these are plane polarized and cross polar images. So you may have some olivine, some pyroxenes, and these ones are small gnats of plagioclase. And all this dark part, this black part here, this is the glassy ground moss. So all this usually undergoes recrystallization. And on the right hand side, you have the QAPF diagram where basalts and andesites were plotted. See, they are mafic rocks. So now, can you see this slide? The next one.
There is a lag, I think.
Now,
Now it has come, yes.
every time I have to escape and do it. Okay. So as I said, the supracrustal belts, they also contain ultramafic lava flows, which are called komatiites. Komatiites, as I said, these are ultramafic lavas which are restricted to the Archean when the Earth was much hotter. Now, a characteristic feature of these comatiites is how they appear on the on the surface, on the weathered surface. If you look at this image to the right hand side, you can see this long bladed features or structures in the rock. Can you see, all of you, these lines, these light colored lines? Sometimes they are crisscrossing, in other cases they are just long bladed.
You look
All
at the upper
lines.
right corner.
Upper right, you have this crisscrossing, or in the center also you have this very long white colored. They appear almost white. These linear features. Can you see it, all of you? Yes or no?
Yes, sir. Yes.
So you say that yes, sir. You have to pay money to say yes also. So you have these features. These are these long, bladed features. These are essentially crystals of olivine. Okay, they look like these blades of this grass that is shown on the left hand side. So this grass is called spinifex grass, and that is why this texture is called spinifex texture, or you have spinifex olivine. So this is the characteristic feature. This happens when ultramafic lavas, they quench rapidly. They quenched rapidly. Now, can you see the next slide?
It is now there.
Yes.
Yeah. So this happens when you have a rapid quenching of ultramafic lavas, as a result of which, the olivine does not get time to, grow to equant euhedral crystals. Rather, it grows to long skeletal crystals. Sometimes you may have crystals as long as a meter in length. So the left-hand images that are shown, this is how these olivine crystals look like in a thin section. You can see these long bladed crystals of olivine. Of course, most of them have now been replaced by secondary minerals such as serpentine, etc. But the original, the shape, because the serpentine usually pseudomorphs the olivine, preserving the shape of the original olivine crystal, but it's mostly serpentine. So these are comatiites. Okay, now can you see the next slide?
Okay.
Yes, sir.
So okay, so now if you look at the sedimentary rocks that you have in the supercrustal belts, you have two types of sediments. Okay, so the first type of sediment includes chemical precipitates from the seawater. Okay, so you had oceans in the Archean times, and from these oceans, you had chemical precipitates which go on to form a special type of rock
And
called.
remember these all these photos you are seeing. These are all from your this Singhbum Craton, not taken from any some foreign photos or some from some books. So
So
these
these,
are all we have taken from the field. So they are really present in the Singhbum.
so the chemically precipitated sedimentary rocks. These include cherts. Now, cherts are, I think, very fine cryptocrystalline SiO2. Okay, that's chemically precipitated from the ocean water. And quite often, these chert layers are interbanded or interlayered with layers rich in iron oxide. Okay, so if you look at this image, the charts are shown. Some of the charts, these two images, on the top one and the left one. These are all images
Yes.
of Archean charts. They
The,
look like almost volcanic glasses.
hmm.
Hmm? No,
And they can have many different colors. So don't be confused by color.
they can be green, black, they could be reddish, so you can have many colors, and they often you will recognize them by their glassy appearance, conchoidal fractures, very fine grain. You cannot see grain size, and quite often they show a very prominent bending. You can see the bending here. So these charts are often interlayered or interbanded. If you see the lowermost image, You can see rock with alternate, layers, red colored layers and brown colored layers, deep brown colored layers. So here, the reddish layers are the chert layers, and the chocolate brown layers are essentially layers rich in iron oxides. Okay, so these iron oxides are also chemical precipitates. So this kind of rock, where you have alternate chert-rich and iron oxide-rich layers. So the iron oxides now they are mostly magnetite or hematite. It's still not clear what they were originally when they were deposited. So this kind of rock is referred to as a banded iron formation or BIF. These are all chemical precipitate from the ocean floor, and people use them, okay, to reconstruct ocean chemistry and so on, etc. in the Archean.
What
They
is
are
surpri-
also, yeah.
what is surprising is that you see some of the bands are millimeter size bands, the thickness, and
Hmm.
they can continue up to kilometers like that. So the
So you have
continuity.
you have this rhythmic bending, and they could be kilometers thick. And when this banded iron formation weathers away, so in when you have weathering in a tropical environment like you have in eastern India, so what happens is the SiO2, the chert-rich bands, they dissolve away, and you are left with the iron-rich bands. And these iron-rich, they form laterite cappings on top of these rocks. And these cappings, they constitute the most important source of iron ore in most parts of India. So in the Singhbum Craton, so in the eastern parts, if you have heard of the name, you have the Guru Maisani Badam Pahad belt. In the western part, you have uh,
Noamundi.
Noamundi, Koira, Jamda belt. So these are belts, supracrustal belts, where iron ore is mined from many of these banded iron formation. So these banded iron formations, the unaltered ones or unweathered ones, can contain up to 30 to 58% of iron. And once they weather, the iron-rich cappings, they can contain more than 78% iron. So they are a very good source of iron. Yeah, Prasiddha, anything to add
Hmm.
here?
Yeah, no problem. Yeah, you can just continue. Huh?
Okay. So can you see the next slide, all of you?
It is visible now.
Yes, sir.
Okay, good. So this was, so far we have looked at the major rock types that you have in the Archean Cratons. And now let's look at some of the rocks that you have in the North Singhbum Mobile Belt. Okay. So as I said, the North Singhbum Mobile Belt, okay, is the area between the Singhbum Craton. I have roughly marked it here. So below this lower red line that you have, that is the Singhbum Craton. Below that, above the upper red line, that is the Chota Nagpur Mice Complex, and in between you have yeah, the North Singhbum Mobile Belt. Now the North Singhbum Mobile Belt, it's an arcuate belt of mostly Paleoproterozoic to some Neo-Archean, green-schist to amphibolite species, volcano-sedimentary succession. So, okay, so this is how you describe it. So you have rocks of mostly Paleoproterozoic to Neo-Archean age. They are metamorphosed at green-schist to amphibolite facies conditions, and the major rock types that you have are volcanic and sedimentary rocks with some intrusives. And it's divided into two parts. Okay, two parts. The by what is referred to as the Dalma meta-igneous belt, or which is also called the Dalma arc. So this Dalma arc I have marked here roughly with this dotted yellow band. Okay, so there's a band of rocks. You can see it's folded on a large scale. So this is called the Dalma meta-igneous or meta-igneous band, or a Dalma arc. So this is thought to represent an island arc. Okay, to the south of the Dalma arc, the part of the North Singhbum mobile belt is called the southern North Simbu Mobile Belt, and to the north of it, you have the Northern North Simbu Mobile Belt. So SNSMB and NNSMB, Southern, Northern. This distinction has been made because there are differences in the geological and tectonic history of the two parts of the belt, because they have formed and accreted at slightly different times. Now, from south to north, the North Simbu Mobile Belt has been divided into four major groups of rocks. So the southernmost group is called the Dhanjori group, and then we have the Chaibasa group. So both the Dhanjori and the Chaibasa group constitute the southern part of the NSMB. And after that, you have the Dalma group, okay, which forms essentially comprises a sequence of meta-igneous and sedimentary rocks, which is called the
Volcanics basically.
volcanic rocks, and also some sedimentary rocks, okay, deep ocean sedimentary rocks. This is called the Dalma group. So, and to the north of the Dalma group, you have the Chandil formations. Okay, so now if you look at the geological history of the North Simbu Mobile Belt, so the sedimentation is thought to have begun already in the Neo-Archean. So somewhere from at about 2.7 GA, and it started with the deposition of the Dhanjari group at the margin of the Singun Plateau, okay, close to the margin of the Singun Plateau. Now this Dhanjari group mostly comprises of mafic and ultramafic igneous rocks, quartzites, and thin patches of conglomerate, etc. And they are thought to have been deposited in a very shallow intracontinental rift setting. Okay, so essentially shallow depositional environment. In contrast, okay, now can you see the next slide?
Okay.
So after the deposition of the Jori's group, then you had the deposition of the Chaibasa formation. The Chaibasa formation involves shallow to deep marine species. Okay, this was deposited already. You had a basin which had formed there, and the Chaibasa formation rocks also comprise mostly of quartzites, siltstones, etc., and they are intruded by granite or a granophyre called the Arcasonic granophyre at 1861 MU. So in other words, the Chaibasa formation rocks were already deposited by about 1861 MU. So this is the minimum age of the deposition. And then after that, you have the deposition of the Dalbum, Dalma, and the Chandil formations over the Chaibasa formation rocks. Now, recently published Zircon age data indicates that the Dalbum formation was deposited after about 1.76 GA, whereas the Chandil formation, which is the northernmost unit of the North Simbu Mobile Belt, that was deposited before 1600 millennia. In fact, sedimentation, okay, in the basin ended or terminated by about 1600 millennia. So you had a long history of volcanism and sedimentation stretching roughly from about 2.7 GA to about 1.6 GA. So this is broadly in a nutshell the geological history of the North Simbu Mobile Belt. And if you try and imagine, a tectonic cartoon which could explain the geological history and the accretion processes that may have operated in this region. So you can think of a scenario, before 1.64 GA, where uh, possibly two subduction zones
Versus you
between.
have to go to the next screen.
Okay. So is it visible now?
अभी ठीक है.
Okay, so if you can think of a possible tectonic cartoon which can visualize approximately the geological history. So you can think of a scenario where before or prior to 1.6 GA, you had a basin with possibly two arcs operating, one where Singhum, the oceanic lithosphere of the Singhum Craton, subducting beneath another oceanic lithosphere, producing this the Dalma ophiolite or Dalma arc, and then you had the sediment and subduction of this oceanic lithosphere beneath whatever continental crust you had in the Chotanagpur ice complex. So this produced the granitoids, etc., that you have in the Chotanagpur ices. And then uh, at about 1.55 GA, now you had the accretion of the southern part of the NSMB and the Dalmar with the Singhum Craton. Okay, this led to the deformation of the sediments that you have in the southern part of the NSMB. Okay, so when this happened, no subduction was still continuing on the other side, no, between the Chotanagpur ice complex, and this you still were depositing all those rocks which were possibly the Chandel Formation, etc., to the north of the North Sindhu mobile belt. And by about 1.45 GA, okay, by about 1.45 GA, so you start accreting the northern part of the NSMB with the Chotanagpur ice complex and the Sindhu Craton. So this led to the deformation of these metasediments and volcanic rocks that you have here. So you have at least, and finally, this subduction stopped, and finally, roughly at about 1 GA or 0.96 GA, you have continent collision between the Singhum crater and the Chotanagpur ice complex. This is when, yeah, the this is when the last deformation and metamorphism of the North Singhum mobile belt happened. So you have at least a minimum of two-stage or 2 to 3 stage history of uh, tectonism and amalgamation in the North Singhum mobile belt. Okay, so let's look at some of the rock types that you have in uh, the sedimentary rocks that you have in the North Singhum mobile belt. So the most common rock type that you get are quartzites or sandstones. Okay, so these are some photographs, field photographs that we took of these quartzites. So these quartzites, okay, you can clearly see this layering that you have. So these are original sedimentary layering. They are often folded. You can see I've shown a fold here. Okay, and parallel to this layering, we have developed a tectonic foliation, schistosity. And this schistosity is defined by alignment of whatever phyllosilicate minerals you have and some flattening of the quartz. So you have, so this layering that you see is not just the bedding plane of the quartzite. So bedding plane. So what is bedding plane? Anybody? Anybody? What is a bedding plane?
Yeah, everybody is thinking Gargi will tell.
There's different layers of rocks, huh? Anywhere you see different layer, it's a bedding plane.
Yeah, this is a depositional layering you see. Bedding plane, when you say it is a depositional layering, when sediments are being deposited, different units of these sediments actually are separated by bedding planes.
So
Okay.
bedding plane represents the layer of sediment deposited in the smallest time interval, representing a specific set of conditions. Okay, and you recognize them by either differences in color of the bands or differences in grain size or sometimes even differences in composition. For example, you may have layer of more quartz-rich sediments, then something changes, and then you have more a layer of more mica-rich
Michael.
sediments. Okay, so this is how you can differentiate bedding planes from each other. So, so in this case, so these horizontal layers that you see, there are bedding planes, but not just bedding planes. Parallel to these bedding planes, you also have a schistosity. Okay, very fine schistosity. So that happens when you have a bedding parallel schistosity. That means these quartzites have been isoclinally folded. So, and that is why when you are away from the hinges of the fold, you will have a bedding parallel schistosity. So, quartzite is a rock which is made dominantly of quartz. For those of you who do not know what is a quartzite. Okay. So here again, I have shown some uh, some bedding planes, and quite often you will see that in some places you also see what is referred to as this thing,
Yeah, current building.
current bedding. Hmm? So here you see this. This is a current bedding. Yeah. Okay.
थोड़ा सा ज्यादा लाइट किसी एंगल से शायद दिखेगा. हाँ, ठीक है.
When you see this, yeah, it's going down. It's asymptotic. I think below it's inverted. It's asymptotic below, and so it's not on the. It's not right side up. It's inverted. And in the bottom image, what you also see is that sometimes within the quartzite you see some layers which are rich in mica. Okay, so rich in mica. So these were essentially original. So quartzite is a metamorphosed sandstone. So and the mica-rich layers, these are essentially now pilites. So they are formed by metamorphism of the clay-rich sediment. So you have alternate clay-rich and clay partings or layers rich in clay minerals, which are interlayered together with the quartzites. Now the other okay. So now your Pusat sir will explain this. So it's his favorite rock. Huh? So in many of the so sandstones or even more, if they are more fine grained, they are called siltstones. So you see this kind of structure. Okay, so these are this kind of where the sedimentary layering is extremely disrupted, undulose. Okay, can you see this? Very fine. The sedimentary layers are undulose, deformed. So these kind of structures, sometimes they appear like flames. Like, so these
They
are
look like as if folded, but we do not call them folds. So why we cannot call them folds? Can you tell me? See, this is not folding. This has been deformed, but these layers are not folded basically. So why we do not call them folding or folded? Because structurally, you see, I'm just explaining, so you don't have to answer then. So structurally, if you see the fold or foliation planes, etc., they are penetrative structures. Okay, so at least if you see that if all the layers are similarly folded, then you can say that all the deformation or bands, etc., are parallel to each other. Then you can say that, okay, these are more or less, these are folded rocks. But here, you just see nearby beds or layers, they are totally different actually in their deformation pattern. If you see, then they are totally different actually. So that is why they have not been folded by any tectonic event actually. So this is not, you cannot structurally, you cannot say that it is folded.
you
What,
see them only in some patches of the rock. Other patches do not contain them.
and even you see that where that blue pen is there, below that on the right hand side and on the left hand side, you see the both the layers, you cannot compare them. The the right hand side layer, you can see that folding is much intense compared to the left hand layer actually. So had it been tectonic folding, both of them should have been similarly folded, but it is not so. So sometimes the tigmatic folding is there, but that is different. And there you have the competency difference, but here no competency difference. All the parts of the rock exposure, what you are seeing, all of them are quartzite. Still, you do not have this similarity in the intensity of folding. So that is why they are not basically structural folding. You can imagine that suppose a layer is there, it is still wet, and because of some disturbance, it just slided down. So crumpled. So that sort of folding it is. It is crumpled actually, basically. So
So
somehow
this kind
actually,
of
okay.
structure, this is called penny contemporaneous deformation. Okay, this happens when you deform a layer of sediment when it's still not compacted enough during just after deposition. So it's still not a compacted rock. In that case, you deform it. Some parts slump, some parts get folded. Okay, or uh, uh, and they slide past each other. So
And
these are thin sedimentary structures.
yes, during sedimentation, it has not yet solidified. The rock had not yet solidified, and then this maybe because of some disturbance, and as we already have discussed that these were mobile belts and some sort of subduction was going on, and whenever this sort of subduction is going on, you expect that time to time there will be earthquakes. And
So these, yeah. So these
so
are all indicators of paleoseismicity.
yes.
Hmm?
So you just something is semi-solid, some sediment, and shake it. So liquefaction of that layer will take place. Even sandstone also, sand layers, liquefaction takes place when you slightly disturb the sediments. And in that case, they will be flowing, they will be compressed and then squeezing out somewhere. So that all these things is represented here actually. It is had we gone to the field, then it would have been easier. But okay, you can understand that this is something like this. And this place is where it is exposed, this layer, it was a actually British time that what is that aerodromes,
Airstrip. Airstrip. Yeah.
airstrip actually used for British Army during pre-independence time actually. So it is near Dalbumgarh.
Near
Okay.
Ghatshila. Near Ghatshila. Those of you have heard of Ghatshila. So here, if you see in this, you see this slump structure. Okay, so this happens when just a part. If the sediment is still wet, as your two sets are said, and just one part of that layer slides down. You can see here in the center, you have this layer. Can you see that? दिखाई दे रहा है?
इसलिए
नहीं,
ओके
अगला स्लाइड दिखाई दे रहा है?
हाँ दिखाई दे रहा है लेकिन कहाँ दिखा रहे हो वो पता नहीं चल
Middle,
रहा है
middle.
हाँ यस यस ओके
In the middle part of the image, just in the middle and slightly lower side, you see there is a
yeah
trough.
that brownish spot reddish spot below you see just above
Uh,
that
just
uh,
above that. So
so you can
just
see that layers have come and they have slumped down there on both
that
the
slump.
sides. The continuity of the layers is above actually, but in the middle actually just above that red spot,
It has gone down.
all of them, all the layers have gone down.
So this
So I
happens
had a
when,
question.
yeah.
Yes.
So, like in the photos, I think to me it looks very similar to ripple marks. Then how do we differentiate between similar structures like that?
Yeah, ripple marks, you see, even in the ripple marks, there will be some, not this much of randomness will be there. eh. So from one layer to another, actually, how does ripple marks form actually? You have, suppose a sediment front is there, or current bedding if you see. If sediment is getting deposited, then next batch of sediment comes and slides down that slope. So you have a very systematic actually layer formed over the older sediment. Okay. And
And ripple mark is a three-dimensional structure. It protrudes above.
Yes. Huh?
Huh?
So
This is
that,
a structure. These you are seeing within in the plane of the photograph. It's not that these lines or these layers are standing out. Huh? They
and
may
the,
stand out because of different degrees of differential erosion, but actually, these are just
layers
layers
actually.
in the rock. Okay,
Ripple
and
marks
ripple
are
mark
on the
is not the
surface
layer
only. Huh?
on the surface. Yeah.
Okay, sir.
Okay. So these are all examples of they are called penny contemporaneous deformation structures. In this case, this is called a slump structure. Yeah, these are all created when you have compaction or liquefaction of sediments
Sediments.
while they are still uh, semi-solid, and usually when you have a earthquake or paleoseismic activity.
Yeah, it is a close up. This one you can see a close up of that. Huh?
Yeah, so here this is another image where you can see these layers. Okay, and many of them they look like when you have a flickering flame. How the flames, smaller, larger ones uh, as the fire burns, you produce flames of different sizes. So they just look like flames. So they are also called flame structures. So
And you can see now that it is not ripple marks. Huh? You see, it is not just surface expression.
and you will see that if you look at this, the central part towards the left central part, here you have this penny-contemporary deformation structure, but
Yeah.
just next to it you don't see it you don't see it. This is just the normal layers continue, so you only see it in some parts, depending on which part has slumped respect to the others. So those parts will show more of this deformation structures. So these very nice features that you can see here. These are dominantly found in the Dalbungar formation. What Prasiddha, anything to add?
नहीं ठीक है आगे चलिए.
Okay, this one.
Here actually you can see what we wanted to show here, that where the coin is there you see. Just something actually has squeezed out on both the sides you see. Can you see the left of that coin? That one depression is there, and through that actually fluid has been expelled out towards the top. And because of that expulsion of the fluid, all the sediments have been entrained along that escaping fluid. That is why you have that just left of the this coin. You see there is a pointed structure actually. You just continue with the lighter band. You'll see that it has become pointed towards the top. It is slanting to the right. So that is because of when this liquefaction was taking place and the sediment layers were being disturbed and squeezed, so the fluid has been squeezed out through that. So that sort of thing also, they yeah that is one particular flame you can see. And so you just see one individual flame there.
Yeah, so they resemble like chaotic folds that you get uh, during solid state deformation, but these are not produced by solid state deformation. They are produced when the sediments were still semi solid or semi fluid.
Hmm. Okay.
Okay, so so now what happens to the, so as I said, the North Sea mobile belt contains quartzites, contains phyllites. So what are phyllites? Now phyllites are metamorphosed clay-rich sediments. So now quartzites are dominated by by quartz, and quartz is very stable during metamorphism, so nothing happens. So quartz just recrystallizes from a sandstone to a quartzite. But in the pellitic sediments, that means the clay-rich sediments, they undergo a sequence of mineral transformations, and when undergo progressive metamorphism to green schist and amphibolite precious conditions. And so if you look at this photograph here, this is an image of a paletic schist which has undergone metamorphism to amphibolite facies condition and is characterized by an assemblage of garnet. So all these pink dots, can you see these pink dots in the rock? All of you?
They are very small, but they are protruding out, you see. So they are like,
Can you see this pink or brown, whatever
Yes,
color
sir.
you call it?
they are looking like nodules.
The circular dots that you see. Yeah, these are all the mineral garnet. Garnet. And have you heard of garnet? What is it? Don't say it's a mineral. What kind of mineral is garnet? Anybody? Silicate. Great. Okay. What kind of silicate? Anybody remembers the formula of any garnet?
So tetrasilicate,
Huh?
SiO4.
Tectosilicates. No, these are not tectosilicates. You find out. We will ask in the Viva. Okay. What kind of silicate is garnet? So it's garnet. So in this case, you have mostly pyropen almandine, mostly almandine
maybe
and
the
pyrope
verses, maybe in
garnets.
the next slide they can see bigger ones, I think.
Yeah, so I will just show it. So you have these garnet crystals, and then you have a schistosity defined by essentially biotite, muscovite, and alternate layers of biotite, muscovite, and quartz. Okay, some places you have formation of staurolite. I don't think you can see it here, but let's see in the next slide. Here, so it's just a bit. It's a close up of that, the same rock. Now, can you see the garnet crystals?
The brown ones, reddish brown ones, and big.
Reddish brown or pink or whatever you call it. So these are garnets. Okay, these ones, and then the rest of the rock comprises of mostly muscovite, biotite, and maybe chlorite, and layers of quartz. Okay, so this is a typical garnetiferous mica schist, which is found in the Singhbum shear zone, close to the contact with uh, the Singhbum craton. Now, these garnets, I don't know if you can see it. I've tried to show it, but I don't know if you can see it. Okay, what you see is that if you follow the phases of the foliation, so the foliation here is roughly along the direction of the pen. Can you see the pen, all of you, in the left image?
Yes, sir.
So
So
we'll
there is
see some lines parallel to that pen. So because
so
the foliations, there will be the traces of the foliation you can see, which is parallel to that pen.
it's northeast southwest oriented. Okay, roughly parallel to this pen or pencil, whatever it is. And what you notice is that this foliation, it just wraps around the garnet. It just goes around the garnet. That means the garnet does not truncate this foliation. It just wraps around. The foliation just wraps around it. So these kind of garnets, when you have the foliation wrapping around it, you can see it here in the topmost garnet here also. You can see here this dark colored biotite band bends around it. And you see the topmost big garnet. Yeah, just next to this grass that you have. Okay, you can see the foliation wrapping around it. I have shown it with these blue lines here.
It has been drawn. So you can
I've
see
drawn.
that garnet has been slightly rotated.
So this kind of so here garnet. Okay, I forgot to mention. So this this kind of structure that you see in the rock here, garnet occurs as a porphyroblast. Okay, so porphyroblast is a large mineral that is grown during metamorphism. So it grows quicker than the other minerals, and therefore it grows to larger sizes compared to the other minerals that you have in the matrix. So such minerals are referred to as porphyroblasts. Okay, and so here garnet is a porphyroblast or a porphyroblastic mineral, and because it truncates the schistosity, so the biotite muscovite defined schistosity. Sorry, so since the schistosity wraps around it, that means the garnets must have been there already when the schistosity formed, because the garnets they behaved as rigid, minerals, and therefore when the deformation happens during which the schistosity forms, the schistosity just bends around it, and the garnets also may rotate. So such kind of porphyroblasts, okay, around which the schistosity wraps around, these are called pre-tectonic porphyroblasts because they formed before the tectonism or the deformation that produced the
So you,
schistosity.
you can imagine that there were very fine grained sediments, maybe clay or something, which was undergoing metamorphism. So the proper temperature reached when this garnet crystal started forming, but there was no deformation till then. So no differential pressure was being put on those sediments actually, no shearing was there. So the garnets actually just by the thermal change, it grew and it became bigger and bigger. So they formed actually porphyroblasts. And so they were bigger grains surrounded by finer grains. That is why porphyro, that word porphyro. And then when this tectonism took place, they were sheared. And then the foliation came. And then only this alignment of the these plating minerals took place. And, and what Professor Upadhyay is telling is that the garnet was already there. That is why the foliations actually wrapped around them. Right? They were not actually truncated by the garnet. If you had developed the foliation and then the garnet would have truncated some of these foliations. That is what
That would be post-tectonic garnet.
yeah, those will be post-tectonic.
But in this case, they are pre-tectonic because they formed prior or before the formation of the foliation. Okay, I think we are almost
So,
close to the yeah.
Yes.
why are the garnets formed like in this way in round class that we see, and why is it not a continuous band of rock?
No, because you see this when garnet is crystallizing, like suppose you can take example of suppose a solution of salt or sugar is there and you are trying to desiccate that. So initially what will happen, crystals will form here and there, no continuous band of crystals will form. Even when you are drying up a solution which contains salt or sugar. So this depends upon where the right condition for nucleation took place. And once nucleated, all growth will be around that nucleus. So it is a random process actually, you see. In a very homogeneous mass, it is being heated up, and where this crystallization will start, that nobody can tell actually.
Usually, wherever all the nutrients are available to form the garnet, so that is where you may nucleate. And then once you nucleate, you grow that garnet. So you don't form continuous layers because, and the second thing is that all these minerals they have interfacial energy, also called surface energy, which therefore they always tend to develop, well-developed crystal faces because
Yeah,
that tends to minimize the surface energy.
yeah, in case of garnet, similarly in pyrite, so they
Hmm.
always try to form euhedral crystals.
Because that minimizes their surface energy. Okay, so that makes them more stable. So garnet here, this rounded shape that you get is because typically garnet has a dodecahedral habit. Huh?
Yeah, Devasis, you can explain here about two sets of that foliation, if it is possible.
It's in the next one. Hmm.
Okay.
So, in fact, if you look at many of these metasedimentary rocks, they have been deformed multiple times. So it's not that they have been deformed once. You may not see the effects of the deformation everywhere. So when a metasedimentary rock gets deformed, you produce, you know, secondary, tectonic foliation, because the minerals align themselves perpendicular to the direction of the maximum stress. All the minerals which have flaky or platy habit, they tend to align themselves and forming planar structures, so which are referred to as tectonic foliation. Now, tectonic foliation can be of different types depending on the nature of the rock, for example, and the metamorphic grade. For example, so if you take a shale and you go on, if you deform it at very low metamorphic grade, you produce a slate where you have just the alignment of clay minerals and maybe some low temperature phyllosilicates. If you have deformation at slightly higher metamorphic grades, then you produce what is called the schistosity, where you have alignment of phyllosilicate minerals, maybe chlorite, muscovite, and biotite. And at even higher metamorphic grades, if you have deformation, then you may even have segregation of, you know, uh, light colored and dark colored minerals together with alignment. So you form what is called a gneissic layering. So the sedimentary rocks or the rocks of the North Sindhu Mobile Belt have been deformed at multiple times. So in many of the rocks, you can recognize at least three stages of deformation. If you look at this piece of rock in this video, so, so
Yeah, the dark lines they can follow actually.
so you can see one set of lines is roughly north-south, and the other set is east-west. Okay, roughly east-west or slightly slightly northwest. So one set is roughly, yeah, roughly north-south, and the other one is roughly northwest-southeast. So, and the third one is in the plane of the photograph.
So it is top to
Okay.
bottom.
So here, this you can see the two sets of lines. One is east-west, one is north-south, and the other one is in the plane. So we'll just show that now. Here, now you can see here. Okay, so this is in the plane. So this is, yeah, yeah. Oh, you can't see. Okay. So now can you see the still photograph? So, oh, coin.
Yes, some movement I could see, but no.
Acha. So forget it. Okay. So look at this. Now can you see the photograph with the coin?
That is okay.
Okay. So if you see this, you see at least two sets of lines here. One set of line is roughly north-south, and the other set of line is roughly northwest-southeast.
Actually,
Okay.
I'll tell that north-south lines we are not able to see, but you can see the darker lines which are that northwest southeast lines, roughly. But they all of them you can see on the surface some corrugation is there, and some ridges sort of things are there, short ridges sort of things. And if you see carefully, then you will find that very fine north-south lines will be available, will be visible actually. Yeah, you can see at the top left-hand side, near to the top left-hand side, you see that the very fine north-south lines are there. And even where I just near the coin, you can see south of the coin. See, very fine lines are there, north-south lines are there. So what does it mean? Actually, there had been a compression, this perpendicular to all these lines actually. One is that black lines, east-west lines. So a north-south compression would have been there at that time, and another time actually a east-west compression, so that vertical lines were created, and top-bottom compression that will create actually the planes actually this parallel to the face you are
Coin,
seeing
face of the
actually.
coin.
Yeah.
Face of the coin. So you have three sets of lines, and all these three sets of lines, they are actually continuous through the rock. Okay, we are not able to show it. If you see the real rock, you
Yeah.
can trace those lines. So these are all penetrative into the rock. So they are all planes. They are all planes or schistosity planes. So you can have, three such planes being preserved in the rock. That means these are three different deformation events recorded in the rock. Okay, so this is how you identify different tectonic planes. Yes, several sets of tectonic planes, and from there you can infer how many events of deformation the rock has,
Undergone actually.
undergone. Okay, so this is how we see some of the rocks, and finally, the last bit, what we usually do, but we cannot do now, is we go to the field and we try to map out the different rock units. So in a metasedimentary terrain, so what you usually have is you have layers of quartzites, thick layers of quartzites, and in between them you have the layers of say pilites, etc. So these quartzites they stand out as ridges, and the pilites because they are softer rocks, they are made up mostly of mica
Okay.
phyllosilicate. They can be easily eroded away, and therefore they usually tend to form the lower ground, the paddy fields, etc. So, can you see this Google Earth image?
Yes, sir.
Yeah. So all those paddy fields, so these paddy fields that you see here, these are essentially your mica schists. You will hardly see exposure. Maybe if somebody digs a well or there's a deep trench, you might get some pieces. Whereas the quartzites, they stand out as ridges or hills. Hmm? And many of them are being mined actually for building material, etc. So these quartzites, which they stand out as hills, they are folded on a large scale. On a large scale means kilometer scale, and you have to go around looking for these say quartzite bands. So you move along the band, across the band, etc., and you can trace out how these bands have been folded on a large scale. So I have just tried to roughly mark, the folds defined by these bands. I mean, if you look at the thickness of these bands, this could be, 500 meters thick. In some places, in the hinges of the folds, they could be even thicker. So several hundred meters thick. So you just go around tracking the bands, measuring the strike dip all along of the foliation plane, of the bedding plane, wherever you get it, plotting it on the map, plotting the contact between the quartzites and the mica schist. So this is how you do. Uh, this is how you map these metasedimentary units. This is what is called lithostructural mapping.
You can
Prasiddha,
see those.
anything to add?
You can see those blue lines. Huh?
Hmm.
So you cannot maybe the ridges are not so visible or so obvious, but you can see that mining has been taken place. That lighter patches. That is because of fresh mining, and the blue lines are defining the limits of those places actually where the quartz or quartzite band has contact with the paddy fields, and the grayish or greenish are areas are your paddy fields, and dark ones are those ponds sort of thing, lakes, ponds, etc. So water bodies. So you can follow those blue lines. They are defining the folds actually. So the if you can imagine that a sandstone layer would have been just a bed, a parallel bed, and one single layer. But when you trace the outer margins actually, then you see that no, they have been folded, and you can see that
Hmm.
blue lines, inner and outer, both of them are parallel. As I was telling you in that penny-contemporaneous deformation, that they do not match actually the layer adjacent layers. But here, the the contacts, outer contact and inner contact, you can see that they are just parallel to each other. It tells that they are tectonic folding.
This was one continuous band, and you compress it, so they get folded in this way.
So when you do this in the field, you will find out a fold. You can discover folding and faulting also. Sometimes they may have been displaced by faulting. So those also you can find out in the field. So just what you have to do, at least for this sort of mapping, you just trace the boundaries actually, the contact with the one contact of a particular rock, here quartzite, with the that shale sort of thing. So
And the contact between the quartzite and the shale will be a sedimentary layering,
yeah,
right?
which has
It's a
undergone
bedding
now.
plane.
Yes.
And now this bedding plane, you can see it has been folded. Okay, and that's the folding pattern you will recognize when you map or trace the competent layers, the layers which are harder. Okay, which
So
because
in
they
the
would define the shape of the folds.
in the field, basically, what would you have to do is that you take a map of the area, and then you go along that contact and take your reading from your clinometer, that at what position on the map you are there, and plot that point on the map. And you several points when you take, then the fold pattern will come out in the map itself. Okay. So earlier days, you see, no satellite images were there. So that is why now with the Google Map, at least we can show that something like this is there, but it would have been very difficult unless you go and map in the field to show that such folding is there. But the finer details, definitely you have to go to field and see. Okay, Devasis sir.
Yeah, I think we are done. That is all from my side. If you have anything to add. Yeah.
No, so what we have done here actually, you see, we are trying to show you two different land masses. So the Chotanagpur Naisik complex, we are not going into that, but we have the Craton, the Singhbum Craton, and these two continents have collided sometime. Okay, so the cratons have collided sometimes, and the sediments trapped in between them have undergone deformation. So from one end of this mobile belt, and those areas which have undergone this deformation are the mobile belt, and you have sediment as well as volcanics there. And from one end, from the Singhbum Craton to the other end, we have shown actually what things you are seeing. And so you have shallow sediments. Once you have you leave the craton, then you have the shallow sediments, and then the deep sediment. Deep sediments are these shale, etc. And then they have been deformed. So the deformation structures, the that penny-contemporaneous this deformation shows that this area was not steady. It was disturbed seismically from time to time, and that is why this sort of deformation has taken place. So that tells that this area was tectonically active. Okay, but craton should not be tectonically active. Once cratonized means it is stable. But this mobile belt was not actually tectonically active, and then a model we have shown, and that is consistent actually with the scientific studies, that this sort of division is there, that that NSMB can be divided into two parts, and also some sedimentary rocks or supracrustals on the Singhbum Craton. So that is all actually we had shown you. And had we gone to the field, then what would you have done? Actually, this is the Galudi area, Ghatsila Galudi area. What this we are showing is in the this village of Galudi, or township of Galudi, you can say. We would have stayed there and try to trace this boundary between the quartzite and the shale and or schist, and then try to reconstruct actually that how this folding has taken place. But okay, so this is all actually. So you just once you meditate on this, you read that material sent to you, And maybe Sunday we'll have Devasis.
Sunday is fine.
So Sunday, what time you just we can start at?
Maybe 10 to 12. It will not take long. Five
Yeah.
people, one batch.
So you decide who five will be in one batch. Amongst you, you can decide. Total
No, but
25.
they have to come. They have to come together. Either they should
Yeah,
tell them
all five.
beforehand.
Yeah, they can coordinate among themselves, and all five actually. Let us do one thing that from according to your roll number from. Yeah, we can first five, then next five, like that we can do, and uh, we can start at 10.
It should be done by in 2 hours.
Okay, so 10, five people, first five people will be there at 10 o'clock, and maybe after 20 minutes of,
Okay, so it's don't be worried. It's more of a discussion and
yeah.
just a few questions. So
Yeah, but
just
you
to
should be able to answer something, each of
yeah.
you.
Since we have not had proper field work, so we have this is a compromise. So that is why don't worry. We'll be generous enough. But we still have to go through the formality. Huh?
So some three people are absent actually, I can see, or maybe five people are absent.
But those who don't come on Sunday, you will fail. So you will have to do it again next year. This is a golden chance of getting away without doing field work.
So,
Next year you will definitely have
But
field work.
can you actually by tomorrow? Can you actually form your groups and mail me the name of the people in each group?
yes, sir, we will do that.
Yeah, so five of you, one group, make it and then let me know who are in which group. And then I can give you a time actually, each group. I can assign a time and at that time you join the meet actually. Okay.
Excuse me, sir.
Yeah.
Sir, I'm traveling on 17th.
17th means?
This Sunday.
What time?
I have a flight on 12. At 12. 12.
12.
Yes, sir.
So can you not do it at 10 o'clock or something like that through your mobile or
I
something?
tried, sir, but I am not sure about the network because I will be on
Okay.
airport.
So from the airport you can do.
Yes.
So you your group you inform and you accordingly plan what time you can join the meet, all of you, and let me know your the group formation actually.
Okay.
So
And if it doesn't work out for you, we will take a separate Viva for
separate
you.
Viva.
Once you reach home.
Okay, sir.
We'll try to do according to this first arrangement, but if it does not work out, then maybe separately we can do that. Okay.
Yes, sir.
So just you form the group and let me know by tomorrow. Okay, then we'll stop here.
Okay, sir.
Okay. 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 Bye.